Today, I'm going to discuss our project in PhD 723 Multivariate Analysis. And this is to be submitted by yours truly, Gerlie A. Alcantara, and to be submitted by our professor, Dr. Sami. I hope everybody is excited to learn about the problem of multiple comparison. And that is our topic for today. We will dig deeper. What is the problem of multiple comparison and why does this occur? What is multiple comparison? Multiple comparison tests are performed several times on the mean of experimental conditions. When the null hypothesis is rejected in a validation, MCTs are performed when certain experimental conditions have a statistically significant mean difference, or there is a specific aspect between the group means. When will multiple comparison problem occurs? A problem occurs if the error rate increases while multiple hypothesis tests are performed simultaneously. Due to this, there is a higher chance of finding a false positive. Consequently, in an MCT, it is necessary to control the error rate to an appropriate level. Let us try to see the different types of erroneous conclusions in statistical hypothesis testing. So we have here HO, which is true, and HO is false. We have here type 1 error and type 2 error. What is type 1 error? A type 1 error occurs if one rejects the null hypothesis when it is actually true. And type 2 error occurs if one does not reject the null hypothesis when it is false. How does the multiple comparison problem impact statistics? For example, for the multiple comparison problem, if we have 5 treatments to compare against each other, then there is a total of 10 tests to perform. With so many tests, there are likely to find by chance, and if nothing is really different, at least one significant result, a false positive. This is where we can correct our testing procedures for multiple comparisons through considering a lower significance level. This has the disadvantage of reducing our statistical power to detect some real differences. A while ago, we are discussing about the significance level. So let us try to see what is the meaning of a significance level in statistics. A significance level refers to a value, say alpha is equal to 0.05, that we use to decide if we should reject a null hypothesis. This alpha value represents the proportion of times that we expect to reject the null hypothesis when in fact it is true. The issue with the multiple comparison is that we are now performing, say, K comparisons, 10 in our case. So the chance of at least one mistake is very high. The formula for the calculation of this mistake expressed as the experiment-wise significance level is AF is equals to 1 minus the quantity 1 minus A to the power of K, where K represents our 10 cases, and which is equivalent to 0.401. Hence, with K is equals to 10 tests, there is a 40% chance that we will incorrectly declare one or more pairs of means to be different. If we had a total of T is equals to 15 treatments, what do you think is our K comparison? So we need 105 comparisons, for which the probability of at least one mistake is 0.9951. And now I am going to discuss to you the statistical methods to correct for multiple comparisons. Number one, the Bonferroni test. What is this? This test is a type of multiple comparison test to determine which means are different from the rest. Bonferroni test can minimize the type 1 error by reducing the significance level alpha, which otherwise increases with sample pairs. I repeat, type 1 error, everyone, occurs if one rejects the null hypothesis when it is true. I have with me here another statistical methods to correct for multiple comparisons, aside from the Bonferroni a while ago. So here we have Hall's procedure. What is this? This is used to counteract the problem of multiple comparison. It is intended to control the family-wise error rate and offers a simple test uniformly more powerful than the Bonferroni correction. The third method, aside from Bonferroni and Hall's method, we have here Sidak correction. The Sidak correction is a method for controlling the family-wise error rate in the strong sense, and it is only slightly less conservative than the most conservative Bonferroni correction. This test produces a conservative or family-wise type 1 error rate of exactly alpha when the tests are independent from each other and all null hypotheses are true. For positively correlated tests, the procedure is conservative and it is liberal for negatively correlated tests. The fourth method is Tukey's procedure. Tukey's method for multiple comparison is used in ANOVA to create confidence interval for all pairwise differences between factor level means while controlling the family error rate to a level you specify. Considering the family error rate when making multiple comparison is important because when your chances of making a type 1 error for a series of comparison is greater than the error rate for any one comparison alone, and to counter this higher rate, Tukey's method adjusts the confidence level for each interval so that the resulting simultaneous confidence level is equal to your specified. Here, some solutions for the multiple comparison problems. What are these? Number one, you're going to continue with your original significance level. Number two, use an experiment-wise significance level. Number three, implement one of the suggested post-hoc tests. Number four, focus on planned comparison. And let us now discuss these four solutions one by one. Some solutions for the multiple comparison problem. Continue with your original significance level. One option is to continue using your original significance level, say your alpha is equal to 0.05 for each of the k comparison. Yet, we have to recognize that it is likely to result in false positives. Therefore, depending on the magnitude of k, we should expect to report some excess of significant result. Our second solution is to use an experiment-wise significance level. In this case, we will calculate an appropriate alpha, the experiment-wise significance level, based on k events. This means that for all tests we are going to perform, we will set a significance level for an individual test that will result in an alpha F. This is thinking of the experiment as a whole event for which we do not want to report excessive false positive rates. The calculation of this is based on the famous Bonferroni correction. The third solution for the multiple comparison problem is to implement one of the suggested post-hope tests. In order to avoid the above extremes, there are several control methods available. Probably you are familiar with Duncan, Tukey, Chef, Donut, and many other multiple comparison methods that are often reported. They all try to achieve a compromise between no control and full control. This is not the place to describe each of them, but they have interesting assumptions and are worth checking out in detail. The fourth suggested solution for multiple comparison problem is focus on plan comparison. When planning your study, if you define clearly what your hypotheses of interest are, and this corresponds to a relatively small number, then it is understood that you do not need any correction of your significance level. The key here is that you're focused in just those pre-planned comparisons. Second, there are integral parts of your experimental design. And the third, you will not perform additional comparison after exploring your data. As a summary, as you have heard, the key for any of this study is the specification of the hypothesis of interest before you do the analysis. And even before, it's better you start the experiment. It is at that moment where the level of risk you are willing to commit is decided upon. And note that that does not have to be the traditional 0.01, 0.05, or 0.10 levels. Here, you determine the risks according to the study objective, the stage of research, and the current and the potential future uses of the study results. Finally, you also have to consider that your decision to control or not to control the multiple comparison experiment wise significance level will likely create some conflict or disagreement between you and other scientists, reviewers, and or your target audience. In order to avoid this, is always recommended that you report all results. This includes the treatment of averages or differences, the size of the effect, the measure of variability, and the full set of p-values. Lastly, I want you to check out these references. Thank you so much, everyone. I hope you've learned something from me today. Goodbye.